Greetings everyone, this is Nick Losee and Caleb Unger. Together we will be doing an 8-part series where we'll discuss concepts of simulation and its applications. Simulation and Monte Carlo with applications in finance and MCMC. This is a great resource that we've been using. So let's now move into some definitions. Greetings everyone. A simulation is essentially a controlled experiment, and these can usually be conducted by a computer program that utilizes the use of random numbers. Now, these random numbers are uniformly distributed between 0 and 1. When we use random numbers, oftentimes we have to use random number streams. A simulation is essentially a controlled experiment, and these can usually be conducted by a computer program that utilizes the use of random numbers. Now, these random numbers are uniformly distributed between 0 and 1. When we use random numbers, oftentimes we have to use random number streams.
So starting with the first type of simulation that we are addressing, we look at discrete event simulation. The reason this is called discrete event simulation is that this type of model usually focuses on distinct or finite events that take place at a particular time, or they can be separated, they can be counted almost. And this could be anywhere in a real-life process or a healthcare facility or a system, anything like that is where we're looking at discrete event simulation. One of the defining characteristics of this type of simulation is that in between events that we are observing or simulating, we assume that there is no change in the system. This allows the system to jump from one event straight into the next event to give an accurate picture of the process that is taking place. So something we could look at would be like births in a hospital. We're looking at how many births or the time that it takes to go through that process in a hospital, or maybe even the time of stay in the ICU. One of the examples also that we found from one of the sources in the bottom right hand corner of the screen is sales seasons, and they made the disclaimer that usually this is known as discrete because you can count the different products over the time they are sold. This moves us into the next type of simulation, or continuous event simulation. The reason we call it continuous is because this type of simulation focuses in on a relationship that isn't really disconnectable. It doesn't have gaps in between the system, and there's a reliance on another variable, or we can say that there's usually a relationship that can be represented in some type of mathematical formulation. A popular type of continuous event simulation would be any type of modeling with differential equations, simulating using those. Now, the events, like I said before, would be impossible or near impossible to count, unlike the discrete event. And so when we're looking at the phenomena that we're interested in, usually we have to simulate it according to the relationship or mathematical equation over a given value that we're given for the relationship between variables. Examples of this would include like a predator-prey or population relationship, or even like how electricity flows through a system based off of given variables, energy use in that system, or any like logistic relationship that concerns growth over time, because these relationships are mathematically formulated, they cannot be separated. Then we get into a different type of simulation, one that is the focus of this class, called Monte Carlo. The reason that we're looking at this is because you can evaluate some pretty complex problems with Monte Carlo when no other approach is actually useful. It deals with systems that are stochastic in nature, that need to have a random generation and some type of distribution that we can generate numerous iterations from random sampling to run it through computational algorithms that produce a numerical approximation or results for a variety of potential outcomes. Again, this relies heavily on random sampling and is very useful in optimization, integration, and determining probability distributions of a given system. It can address problems with high uncertainty with multiple degrees of freedom, and also any problem that has some type of probabilistic interpretation. Now, what is different about Monte Carlo than the other methods is that we are using simulation in such a way that we're generating many random samples. That is one of the defining characteristics of Monte Carlo simulation. Moreover, we're running it through several algorithms over these numerous iterations to get approximations or probabilities that an event would be likely to occur, unlike already having a systematic way of running it through like a differential equation. We're really looking for how the relationship could pan out according to computational algorithms over a random sample, rather than observing a discrete or separated event or modeling something according to a mathematical law or algorithm that's already in place. Therefore, some of the examples that could be addressed using Monte Carlo would be varying levels of environmental risk assessments based off of very wide ranges of variables that could go into that, and also like predicting server behavior, like internet poker, when you're looking at random generations of numbers and then all of a sudden you can guess the pattern and what they're doing based off of the probability of occurrence over many iterations. They've also used Monte Carlo in determining behavior in particle physics and also business policy performance based off of many iterations. One example that we did in class is you can use Monte Carlo to estimate pi by generating numerous points within a sector, and then using basically the definition of a circle in order to determine the relationship or an estimate of pi.
Alright, so we're going to conclude with a brief history of Monte Carlo simulation. So if not for the lovely game of solitaire and Stanislaw Ulem's illness in playing solitaire, we wouldn't know simulation the way we do it today. In their attempts of modeling neutron diffusion and radiation shielding, this method, codename Monte Carlo, was produced, which essentially, is... Alright, so we're going to conclude with a brief history of Monte Carlo simulation. So if not for the lovely game of solitaire and Stanislaw Ulem's illness in playing solitaire, we wouldn't know simulation the way we do it today. In their attempts of modeling neutron diffusion and radiation shielding, this method, codename Monte Carlo,